Cool. So let's begin. So this talk will be focused on how GitLab scaled or Git access and Git storage using a Go service. My name is Oswaldo, and I'm a backend engineer on GitLab. I'm from GitLab, and I work on the creates team. So this team is mostly focused on merge requests, the code reviewing part of the code base, web IDE as well. And yeah, I enjoy hunting performance bugs, performance issues on GitLab. And I moved to São Paulo like about a year ago. And if you'd like to just talk a little bit about performance and all that kind of stuff, and GitLab as well, about features, feel free to just reach me. So today we'll cover what exactly GitLab is. There's someone that uses GitLab in the company. Cool. So what GitLab is and how GitLab uses Git, and how GitLab scaled Git storage and access, as I said. A few limitations that we saw with the first approach, and then we iterated on the tryouts. A little bit about Gitaly, the service that we created. And this service is composed by gRPC, that we are going to talk a little bit more, protocol buffers that comes with gRPC, and Prometheus for monitoring. And we'll talk a little bit about how Gitaly fits into GitLab. So basically, just first to give a head start, basically GitLab started as a self-hosted application, and then we started moving towards GitLab.com having access. And we have today Git repository hosting, code reviewing, and CI/CD monitoring, and security testing out of the box. So it's cool. We have a bunch of open source projects. So basically all the codes that I'll show today is basically open source. And just the EE side that we have, the enterprise edition, that needs a license for that, but the other projects are mostly in open source. So that's a photo from the last contribute, a bunch of people, New Orleans. It was really nice, by the way. And yeah, as I said, it started as a self-hosted company, and then we focused on the SaaS later on, GitLab.com. And today we serve around 3,000, we do around 3,000 Git operations per second. So it's scaled really fast. And we release a new version every 22nd, every month. So at the beginning, GitLab.com was running in a single server. So imagine a typical Rails application, right? You start over and you have your unicorn, you have Sidekiq, you have Git storage, you have a bunch of stuff in a single server. And it's easy to deploy and maintain, but it's really hard to scale, right? So to put everyone in the same page, vertical scaling, we can reach some limit at some point based on the hardware that we use. And horizontal scaling, we would be able to keep adding new servers horizontally, so that we could spread the load between those servers. So we ran out of options to scale GitLab.com because it was running in a single machine, and the whole infrastructure was focused on that as well. So it had to be made possible. So just bringing it up, a fun fact, we have a blog post about it. And we use it to run our own hardware. And we had like 100,000 repositories at the time. It was early 2015. And yeah, we had to move back to the cloud, right? Because at some point, it's hard to maintain a data center, for instance. So this talk will be focused on Git storage and how we access actual Git data. So just a brief overview on how we use that. basically we use a gem called Rugged that wraps a libgit 2. That's the implementation of the Git core methods. It's in Ruby, so there's the libgit 2 in the C, and Rugged is basically a wrapper around that. And we also use Git directly from the command line. And over time, we started consolidating this Ruby API for the people on the team to use and be more comfortable just fetching this data and implementing new features. So let's talk a little bit about the horizontal scaling. At this point, we were just adding money to the problem, let's say. And then we started thinking that we would need to scale this horizontally. So let's say we would need to separate repositories in different NFS servers. So NFS server is basically a protocol that you can access remote files in different servers. So let's say you have a unicorn server. Let's say 3 separate unicorn servers. And then we would have these 3 different Git servers that we called it at the time. And these servers, Git servers, would have NFS. And the way we use it to access these files were mounting every NFS server in the clients, the application servers. So let's say we need a new Sidekiq instance. We would need to mount all those NFS servers in the Sidekiq as well, because we needed access to those repositories. So we started seeing a few limitations with NFS. First of all is latency. We've had a little bit of overhead with NFS because NFS adds some latency to the I/O and the remote system calls. And it's a shame because if you use Git locally, you can see that's fast, right? It works really fast, and we were expecting this to work like that in your remote environment as well. So with NFS, we had this extra time to deal with. So let's have an example of how we would fetch branches for this repository, for instance. At the time, we had this Rugged. We were using Rugged to fetch those repositories, and this example, we are going to fetch the branches. So there's an output. I believe it's a little bit harder to see. But in the first part, we are reading this folder called git packaged refs. So we are fetching branches. So basically, all the branches of the GitLab CE, for instance. So for each of those refs, we would do a system call lstat to check if this ref actually exists. This is on system level, right? So underneath, we were doing actually I/O and adding latency. So let's say we have 1 millisecond latency, and we have 2,000 refs. That would be just 2 seconds spent on I/O and the trip to the servers. So that isn't really nice to have. So the system also showed that it was not very fault tolerant, and we had low visibility at the time of the problems that we had. So for instance, something that happened more than once on GitLab.com was that we were having this exact same strategy, and then when an NFS server goes down. So the problem with that is that the connections, the client connections with the server would just hang the server completely. And it's like a very opaque failure because of NFS. And we started seeing some nice graphs on GitLab.com. And these are the workers stopping the response, because if everything is mounted on all those servers, the client servers, application servers, everything goes down. So we started seeing that, okay, we have a problem there, right? So yeah, this is fine, I guess. But yeah, we had a few problems. We had these problems, and also the actual logic of accessing Git was a little bit spread around. We had a project called Workhorse, We have GitLab shell as well. So those are the clients that need Git data. And we also have the monolith. That's the GitLab Rails, because GitLab, the most part of the application is written in Rails. And we had all these parts of the code base having a little bit of logic of how to access Git. And we started seeing, okay, we also wouldn't be able to cache this properly, because if the logic is spread, it's hard to self-contain the logic in a single place and cache. They do a bunch of stuff. So we came up with a better idea. We came up with Gitaly, that would be a Go service that would encapsulate all this logic and introducing, being able to introduce cache solutions a little bit more easily. And yeah, keeping the logic in the same place and use interesting technologies to improve that. So a few ideas that would be basically our Git database. We can explain very simply what's the idea behind it. We would use gRPC and protocol buffers, which is a cross-platform RPC, and for well-defined APIs, you can just describe messages and reuse messages and get a more, let's say, strict API. But since it's typed, it's cool because you can just make it more resilient. It won't break from nothing. It would be written in Go, because we had a nice experience writing Workhorse, which is our reverse proxy. And it was very stable, and that was an interesting idea to run with gRPC as well as Prometheus, that's written in Go. So we would use Prometheus for monitoring. So basically the idea was that we would send a request, like imagine a simple HTTP request, but we would send just the parameters that we need to the Git server that would be running Gitaly, the process there, and we would just return the data over the wire. The difference is that we are not running through the NFS latency there in this problem. And the applications would know which server to go to fetch the data that we need. We wouldn't need access to all the repositories at once. So the development side, we actually started a new team just to focus on that. And we decided that we would slowly roll out this in staging and production and using feature flags. So that wouldn't be necessarily flagging the whole Gitaly. We would flag different operations. Let's say we can git fetch, we can git clone. So all those actions are flaggable. So we would be able to just test and see if everything was working well. So going back a little bit, that's the first iteration of the scaling. We would access these NFS mounts directly, and after that we would implement Gitaly in the same server, the Git server. It's nice because we could reuse the repositories in the same server there with NFS. And at this exact point, we would be able to just use the flags, because if it's on, we go to Gitaly. If it's not, we go to the NFS mount. So yeah, that feature flags would save the day at that point. So if everything was running well, latency was great and performance was great, we would just unmount those NFS servers. So underneath, we decided that we would use gRPC, and that's basically an open source message exchanging framework. It's focused on low latency. It's highly scalable. It's also used by Slack and other big companies. It goes with gRPC, with HTTP2 out of the box, which is great for streaming and all that. And it comes with protocol buffers, as I said before. So what's cool about that is that in our case, we would have a Ruby client, which is a backend client, and we would have this Go application that is Gitaly. And with protocol buffers, we could describe what's the protocol for exchanging information between those servers. It's a little bit more strict than a normal JSON API, but it gives a few extra niceties, like being stable on the API. Also cool about that is that these proto requests and proto response can be streamed. So since we were moving around a bunch of data, we could just stream the request and response in a few scenarios. Also cool that HTTP2 comes with streaming. It means that you can use a single TCP connection to send chunked data in the request and response. So that would mean you could fetch a bunch of data and just stream the response in separate batches. It's also cool because it's not non-blocking. So if a package is taking more time, another one can arrive earlier. So that solves a few problems. So protocol buffers. The idea is writing the messages on this proto file, and then you can export with and just compile this code into Ruby, Python, or Java, in our case, Ruby and Go. So for instance, this is a real code that you use in production, and that has a definition of the merged branches. So let's say we want to know which are the merged branches. And there's this, and we built this request there. There's this Gitaly find all branch request. And it's cool because you don't really need to write this code, because this exact code is being generated by protocol buffers. So we are passing a repo, a flag, and the merged branches. And we are also setting the timeouts there. So it's nice because gRPC also handles timeouts well. And we are consuming this response. Since it's a string actually being returned there, we consume this string. So the gRPC, the gRPC definition is there as well. You can define like a find all branches, receiving a request, and we return a string of the response. So you can see there's a repository being defined, the first argument, and you can't see the repository there because it's being reused for somewhere else. And it's great because you can just reuse messages and compose different responses and requests. And there's the response as well, and we are defining the branch right there and saying that a repeated branch would be returned. The repeated would be basically an array definition for the string. So you might be thinking, but why not the JSON API, right? It would be easier. But there's one side of gRPC. We have the performance. You have server-to-server connections working well. And the other side, there's the simplicity of just defining, and people can just browse and see the response. It's easier. And also, there's SOAP, right? Everyone uses SOAP nowadays, right? But we had a few advantages as well, comparing those two, because SOAP, right? So we had a mature interface for interacting with Git. That means we could just port this over, and we would know already what exactly the server needs to be provided. So the arguments would be a little bit more clear for us at the time. So we have server-to-server binary message streaming. So yeah, it's different from text, normal HTTP. Great. We have numbered fields, the definition of the protocol buffers. So that would be backward compatible. We would have this definition being maintained for a while. So that would mean if you wanted to just go back in a version, that would be staying there, working as expected. And also you can export for different servers. right? But I want to see graphs, right? Everyone likes graphs. So in that part, we are solving the problem of visibility right there. So first we need to collect this, right? And again, Prometheus. And yeah, so Prometheus was created by SoundCloud, and it's an open source project. It's written in Go. It's a time series based monitoring. So you can imagine that as snapshots. So imagine at this point we have this amount of things, let's say orders, and at this point we have X amount of orders. And that's basically snapshots. And then you can plot these snapshots into graphs and use nice language to query, like PromQL. It also handles alerting, so meaning that you could write some nice code to check if there's a bunch of orders at this point, we want to alert about something. So it's great for monitoring, not so great for general logging. So that's not a tool to just try to log different messages being text. It's based on numbers, basically. So like error ratio, request ratio, it's nice to know if the cache that you implemented is hitting or it's missing a lot. So these kind of things are really nice. And we use it to check, for instance, if the cache hits is working. So there we have just a brief overview of the architecture. At the center, you can see there's a Prometheus server. And it's based on pool model. So instead of the other servers pushing the information to the Prometheus just pulls the data. And that's cool because if a server goes down and it pulls the server, it knows it's not working well. So you have a little bit more visibility on this side. Down there we have the jobs exporters. So basically that's the servers that they would be fetching the data from a metrics JSON, I believe it's JSON endpoint. And you have the push gateway. That's the only few parts that Prometheus push data. And that's for, let's say you want to just spin up a process really fast and just monitor something and just push the data to just plot a graph after this. And that's the idea of push gateway. They just spin up a process, push this data to push gateway, and then Prometheus can just fetch this and persist. It's normally persisting in memory. That's the idea. It's a memory database. But you can also configure to just go to the disk at some point and just persist that. There's also the service discovery. It's nice because let's say you're using AWS and you automatically creates a new server. That service discovery just tries to understand what do you have in your infrastructure and try to see which servers that would be able, they would be able to fetch, for instance. So a little bit of black magic there. So you can also push alerts, like I said before. You can use a query language. So let's say your server is responding with 90% of failures. Let's say you can just send an ads channel to your Slack and make people happy. Also, it works with PagerDuty. You can also send emails. So also good that it integrates with Grafana out of the box. Also nice. And there's a Prometheus UI. That's it. We are querying for Gitaly cat file cache total, and it returns quite some data there, but it's smaller. But you can see the type there, and that's a duplicate or dirty or hit, and or miss, and we are checking if the implemented cache is actually working. And you can see the numbers going up, and it's great. You can have some visibility. In the query language, for instance, we are grouping by type, and you can see the type down there. So really interesting. So code-wise, that would be written in Gitaly. So we have the cat file cache counter, and we are saying that we have a label called type, and we can add additional information there as well. And we register this counter, and in some place in the code we can just use that, and it keeps adding this counter, and Prometheus would fetch this data later on. So as a summary, after we have gone to Gitaly, we saw faster message exchanging, which is a good point. We had reliable typed interface, so it would be a little bit more strict, but that's part of the reliability of the message exchanging. We had more visibility because of Prometheus. We had self-contained logic, so nowadays we are writing more cache for things that we need, which is also great. So the bad side is that it's a higher entry barrier for contributors. So as I said before, GitLab is written in Rails, in Ruby, and not everyone on the company knows Go. And it's also a little bit harder to get open source contributors to Go, because it's a very specific project to solve a specific problem, and it's written in Go. It's a little bit harder. It's a little bit more complex to maintain, because we have all those different pieces and tooling, protocol buffers to maintain, protofiles, and all that. And funny enough, after running Gitaly and monitoring, we felt a little bit slower. The team said it felt a little bit slower, because since we had such a great visibility, it would be hard to move faster, because we were seeing the actual problems happening, which is a great problem to have. So yeah, I believe that's it. Hope everyone enjoyed it.